Have this question, School Cardinal 2022 WASSCE. The question said the diagram below illustrates a decay curve for a radioactive sample of original number n. This is, so we are given the curve. This is the curve or the graph where in the original number n is given as this, and the next number is 500 and x. But there is one thing we have to take note of. This number, this original number or the initial number decays to give us this 500. And as well as this 500 again decays to give us this x with respect to their time. But this n and the t are related with this equation, NO e raised to minus lambda t. You see, where n is the number of nuclide, this NO is the initial or the original, and this n is the final. This lambda is the decay constant, and the t is the time. Another famous equation we might use here to solve is 2 raised to n equals to NO all over n, where in this n is representing the number of half-lives. If we have 2 half-lives, means n is 2, 3 half-lives, n is 3. So in this case, how can we relate this n with it? Moving, if this initial value or original value decay to give us this, so we have 1 half-life from here to here. In this case, let's just make it in a function. From here to here, from this n to this 500, number of half-life is 1. Also from this 500 to this x, number of half-life is 1. But if you move directly from this number of nuclides to the third one here, which is x, the number of half-life we have is going to be 2. We have 2 half-life with corresponding time 10, 20, and so on. But the relationship between this n and this t, the higher the nuclide, the lower the time. Or the higher the time, the lower the nuclide n. So this is how n and t are related. So the question here is about using the graph to calculate the values of x and n. So how can we use this graph or this curve to find x and n? So in this case, to find x and n, it depends. This is the formula we are going to use. If we consider n is the initial and 500 is the final, therefore this n is going to be the initial and this 500 is going to be the final. So if we do that, let's start to say n, the initial number, which is the starting, NO, is given as n here, and similarly the final n, because since we are continuing from n to 500, and the final there is given as 500. And the number of nucleus n is given as 1, because we are moving from n to 500. So in this case, since we are required to find n, so we use 2 raised to n equals to NO all over n. So we substitute n is 1, and NO is n, and n is 500. So since we are looking for n, we cross multiply. N is going to be 2 raised to 1 times 500. This will give us 1000 atoms. So therefore, n equals to 1000 atoms. You see, so we have the value of n to be 1000 atoms. So now, if we want to find x again, moving also the same thing, we consider 500 to x. Therefore, from 500 to x, simply the initial is 500 and the final is x. So the initial or the starting NO here is given as 500, and the final, which is n, is given as x. And the number of half-lives n now from 500 to x is going to be 1. So we also use this formula, 2 raised to n equals to NO all over n. So we substitute n is 1 and NO is just 500 divided by n is what represents as x. So if we interchange now, x is going to be 500 divided by 2 raised to 1 is same as 2. So this gives us 200 and x is, we have it to be 250 atoms. So this is how we have it. Or if you don't want to use this method, another short way of using that, let's say we move, if we don't consider the 500, we consider n to x. So considering from n to x, it implies the initial here, NO, is same as n, but n now we have it to be 1000 atoms, and the final now, n, is same as x. And the number of half-lives, since we are moving from n to x, we have 2 half-lives from here to 1, from here to 1, so the total number of half-lives is 2. This is it. So if we use this formula, 2 raised to n equals to NO all over n, we have 2 raised to 2, which is n is 2 and NO is 1000 divided by n. So if we interchange now, 1000 divided by 4, so therefore n is equals to 250 atoms. So this is how we calculate the values of X and N. So X is 250 atoms and X is 250 atoms. We have X to be 250 atoms. Here is X. Here is X. Here is X. So we have X to be 250 atoms and we have N to be 1000 atoms. So if we move again to the next phase, number of samples disintegrated. So since we are required to find the number of samples disintegrated after 40 days, let's say we remove the top. So removing this top, so if we move to Roman 2, we are required to calculate the number of samples disintegrated. For us to calculate the number of samples disintegrated is after 40 days, let's have the graph. So since after 40 days, the graph was this. Here we have N, this portion is 500, and we have the other one which is X is 250. So the first time was 10, the other one was 20. But the time for 40 days is going to be, the next one is going to be 30, next one is going to be 40. So in this case, the number of half-life is 4. Because we have from 10, 20, 30, 40. So N is going to be 4. You see. So if you use the same relation, 2 raised power N equals to NO all over N. So the number of half-life here is 4, which is 2 raised power 4. And the nuclei, which is starting, is N. But this N, we have it to be 1000 atoms divided by N. So if we interchange now, N is going to be 1000 divided by 2 raised power 4 is 16. You see. So numbers of atoms, we say number of atoms left. Number of atoms left, 1000 divided by 16. 1000 divided by 16 will give us something like 62.5 in terms of grams. 62.5 grams. But this is not what we are required to calculate. We are required to calculate the number of samples that disintegrated. So number of samples disintegrated is going to be the initial, which is N, minus this final, which is NO. So it's going to be N now, we have it to be 1000, minus the initial, which we just calculated, which is 2.5. So this is this NO minus N. So if we subtract 1000 minus 62.5 minus 62.5, 1000 minus 62.5, that gives us a value of 937.5 grams. So this is this. So this is the number of samples disintegrated after 40 days. Thank you all.